Hi, this program is on entropy. I want to start by reviewing two laws of thermodynamics. The first one we've seen before. Calorimetry is based on this first law. Changes in chemical potential are measured by changes in thermal energy of the surroundings. The second law will be somewhat new to us. The entropy of the universe is always increasing. Well, what's meant by entropy? Entropy is a measure of the dispersal of energy or matter. Let's consider this. Iodine solids subliming into iodine gas. Here we have a picture of a microscopic imposed upon a macroscopic view of iodine crystals undergoing sublimation. We have in the crystal form I2 arranged in a nice crystal lattice structure, and in the gas we have the iodine crystals dispersed or spread out. Generally speaking, the greater the number of gas particles produced, the greater the entropy. We would say in this case, the entropy of our system is increasing, or delta S is greater than 0. Here's another change. Dissolving sodium chloride. Here's a picture, and generally speaking, the dissociation of solids into ions also represents this dispersal of matter. So we can also say our entropy is increasing. This is a mathematical statement of the second law of thermodynamics, that the entropy or the changes in entropy of the universe are always increasing. We consider the universe being broken down into two parts, our reacting system and its surroundings. Here's the reaction of nitroglycerin. Let's take a look at what we think is first of all happening to its change in entropy. We can see we're going from a liquid to a whole bunch of gas particles. So this we can definitely say that the entropy of our system is increasing, or would be a positive value. What about our surroundings? To understand that, we have to take a look at where the heat term is in this expression. We can view this as an exothermic reaction, so heat would be a product. That heat is going to go into our surroundings. When it moves into the surroundings, this results in an increase in speed of the particles in the surroundings. This increase in speed results in an increase in the dispersion of energy. So we can say that the entropy of our surroundings is also increasing. We can see in this type of situation, we're guaranteed that the sum of the two will be greater than 0, fitting our second law of thermodynamics. Let's consider another reaction. H2O gas forming H2O solid. That's the formation of frost. This case, our entropy is going down because we're going from a gas to no gas. So we can be sure that the entropy of the system is going down. But where is the heat term in this expression? Well, this change of state produces heat. The gas particles have to lose energy to their surroundings. This then results, as before, increasing the entropy of the surroundings. However, if we compare the magnitude of these two changes, we do know that they have to be greater than 0. So I would expect that the entropy change of our surroundings was bigger than the loss that we had in our reacting system, because we know that the sum of the two has to be greater than 0. My last one is the reaction that takes place in a cold pack. Again, let's take a look at what's happening to the entropy of our system. We have a solid breaking into ions. That's going to be a positive change. Where is the heat term? Well, it's called a cold pack because it takes heat from the surroundings. This then results in a loss of entropy of our surroundings. But again, to fit the second law of thermodynamics, the change in our system here must be bigger than the change of our surroundings to end up with a positive value. Let's look at how one goes about calculating entropy change. We use an equation that looks very similar to the enthalpy changes using heats of formation, products minus reactants. And we have a table in our IB data booklet, table 13, that has some of these values. Let's work out the entropy change for this reaction. So I consult the IB data booklet and I get these values. What would you expect the entropy change in this system to be? Well, we're going from 1 gas to 3 gases, so we should get a positive value when we're finished. Substitute them then into our equation, and we're multiplying each of the terms by the number of moles present. So I begin with my products, 1 times 151 and 2 times 131. That represents the entropy of my products. What about the entropy of my reactants? Well, I subtract it. The 1 mole of the butane at 310. In solving, I get the entropy is indeed positive as expected, and the units for entropy are joules per Kelvin. To recap, entropy is a measure of the dispersion of energy and/or matter. The entropy change of a system and the entropy change of the surroundings operate in such a way that their total is always greater than 0. And the entropy change can be calculated.